And go. Hey everyone, I really can tell that you guys are ready to go. I'm excited to have you guys here for another Q&A. Real quick, I wanted to mention something that I'm currently doing. So I've been getting a lot of requests if I do online tutoring, and some spots opened up. I've made some more time in my schedule for tutoring. So what I'll be doing specifically to prepare you guys for your finals or just pretty much for any exams that you guys have towards the end, I will be doing online tutoring. So if you see on the screen, it says if you need online tutoring, and go to that site, and it is howtopasschem.com, and then you can sign up for one of my online tutoring sessions, which will actually be next Saturday. I'm going to have two different times. So if you can't make the first time, then I do have another option. I'll specifically be covering thermochemistry. So if you're struggling with, let's say, finding enthalpy, calorimetry, Hess's law, or bond energies, all those types of topics, I'll be covering it all. And basically what it's going to be 1 hour of me teaching all of these different topics and going into detail, showing you different test questions that I've seen overall and explaining them and how to, actually answer them correctly. And then it's going to be for 1.5 hours. So for the first hour, I'll be teaching, tutoring, explaining everything. And then for 30 minutes, I'll be answering questions. So it is a group size of 5. So that's the maximum. So it's a lot smaller of a group, so I can answer so many more questions. So definitely check out that link. It's howtopasschem.com if you guys need more help. All right, so let's get started. Let's go with the first question. Jose is the first one, and he says, the addition of 115 grams of potassium fluoride, so KF, to 607 milliliters of water with a density of 1 gram per milliliter causes the temperature to rise to 3.30 degrees Celsius. What is our change in enthalpy of our solution for KF? Okay. So we're looking for our overall enthalpy in this case. Now, and then it's asking for the temperature to rise. So what I'm basically going to do here is I need to figure out the amount of heat. So a lot of times whenever we're asked to find enthalpy of a solution, we're actually looking for the heat of our overall solution or reaction. So what we're given here, and then let's see what else we have. We're given milliliters of water, and actually I have KF, dropping it in a solution. Let me see if there's anything else that they give me. Causes, milliliters. I'm thinking it is Q of a metal, but we actually have a salt. So let's see what formula I will be using for this first one. Causes the temperature to decrease, or actually to rise. So it rises. Okay. So typically for our change in enthalpy, they should be giving us some sort of formula. Let me see what I can do with this question. One moment as I look for my example. Okay, KF, and then that's balanced. I mean, what I could do was, I just want to make sure I'm doing everything with the balanced equation. If you're putting KF and you're dropping it in water, what this would then form is an acid, and then some sort of base. So that would have been our formula, and then everything is actually balanced, so it's a one-to-one relationship, so that's fine. And then from there, if I'm finding our change in enthalpy, let me see what else I can do. I would change those grams to moles because we will need it eventually. A lot of times when we're looking for enthalpy of our solution, you're going to want kilojoules or some sort of joules, and then divide that by the amount of moles that's given, which in our case, we will have to do moles of KF. So just for the first thing, I'm actually going to figure out the moles of KF and go from there, since I know we're going to need it. We're going to need to divide it at the end. So I'll take 115 grams of potassium fluoride, and I'll multiply that by the molar mass of potassium fluoride. So let's figure that out. So potassium has a mass of 39.10. I'll add that to fluorine's mass, which I think is 19. Yeah, it's 19. All right, so that's 58.1 per 1 mole. Okay. So I'll figure out the moles of Kf. We'll see what we get. I'm just going to divide these two values. And then next I'm going to figure out what the heat is. So we have 1.98 moles of Kf. And then, so I'm going to use that at the end and divide at the end. But the first thing that I'm now going to actually, what I'm now going to do is I'm going to figure out what the Q or the heat is of our solution. So I'm going to use, let's see, MCAT, but this is specifically of our solution. So I need the water. I'm just thinking what we're using. I know Q is equal to the reaction, which is equal to negative Q of their solution. There it is. So this is something that we have to know. Our overall reaction is going to be equal to the negative heat or negative Q of our overall solution. So be aware of that. You will find your overall Q, which is the mass times our specific heat, which it's water, so we do know that. And then this would have been our change in temperature. So what I'm going to do, since they're giving me the actual mass of, actually they're giving us the volume of the water and the density, that basically tells you to convert that to grams. So the mass that we're going to use is of water after we convert it. And then your specific heat capacity is 4.184 joules per grams Celsius. That's something to know. That's specifically of water. And then I'm going to multiply that by the change in temperature, which they gave us, the 3.30 degrees Celsius. And it's fine that it's in Celsius. So I'll plug that in. And then real quick, let's go ahead and figure out, convert really this milliliters to grams, which I know is the same thing, but just showing it. This would have been 1 milliliter per 1.00 grams, since they are providing that for us. And then this is 607 grams. So I'll plug everything in, and then that'll be almost there. We're almost there. So this would have been 607 grams. Multiply that by the specific heat capacity of water. Then I'm going to multiply this by the change in temperature. And then this will give us joules. You'll notice that the grams and the Celsius and Celsius would cancel, giving us joules. We'll multiply straight across, and let's see what we get for our heat. So 607 times 4.184 times 3.30. This is Q. A lot of times they want this in kilojoules, so I'm going to convert that to kilojoules, and this is joules. So all we're going to do is divide by 1,000. And then really what you're doing is you're moving this decimal place over 1, 2, 3. And then this is 8.380. I'll leave it like that, kilojoules. And then lastly, since this is our Q, the last step that I'm going to do is just divide by the amount of moles that we found initially. So this would have been, what were our moles? So dividing by the moles that we had, that was 1.98 moles. 1.98 moles, just because now instead of Q, we're looking for the change in enthalpy, which is, think of it as Q divided by the amount of moles. So of whatever we're looking for, which in this case is Kf. So I'll divide those two values, and let's see what we get. Okay, this gives us 4.23 kilojoules per mole. And that would have been of our overall solution. Let's make sure one thing, the addition of that in water, the only thing that I would state that it would be negative, the only reason for that is because it was that whole Q of the reaction is equal to negative Q of our solution. So that's why this would have been negative, but that's it. That's how we do this question. Okay, so next question is Eleanor. And she asks, hi, Melissa. My question is, which molecule has the shortest carbon-oxygen bond length? Okay, so when we're looking at bond length and whether it's long or short, what we're looking for is the specific type of bond. So whether it be a double bond, a triple bond, or a single bond. So our single bond is going to be the longest no matter what. And then our shortest will be a triple bond. So all you're looking for in these molecules is which one has the triple bond between the carbon and the oxygen, and then that would have been your shortest. So, and then the double is always in the middle. So let's look at these different ones and look at the structure. So A is CH3COOH, and we'll draw this out. So just looking at the Lewis structures, really this is drawn how it's supposed to be, where carbon and carbon will be central atoms, and then your carbon is surrounded by 3 hydrogens. We have another carbon here, and then a lot of times how this is going to be attached is this portion at the end is an OH. Those two will be attached to each other, and then another oxygen will be attached to that carbon. If I were to draw this out, this would have had a double bond, and then really what we're looking for is that carbon and oxygen bond length, and it would have just been a double or a single bond, depending on whichever one you're looking for, like these two. So far, that's not a triple bond, so we're just looking for, is there anything with the triple bond? And this one does not have it, so there's a possibility that it could be another one. So let's look at B, CH3CH2OH. This one's very similar. So this is C and C that are going to be attached to each other. I'm just drawing that CH3. Now I'm going to move on to CH2. So that carbon is connected to that other carbon. Hydrogens are surrounding that carbon. And then at the end, we have that OH, which is still just a single bond. So this is what we're looking for. So nope, that's the longest. I wouldn't say that's the shortest. And then I'll keep going. And then C is CO2. So with CO2, carbon will be our central atom surrounded by 2 oxygens. You'll note that this is going to have a double bond, and then lone pairs, of course. But so far, we just have double bonds. So let's see the last one, which I believe it is. This is going to be CO, so carbon monoxide, so D. Yeah, so this would be the case because we're going to have a triple bond between these two. And then lone pairs, of course. So this would have been, just to kind of help you see this, carbon would have been 4 valence electrons plus 6 because of oxygen. And then that would have been 10. So far we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then this is actually going to be the shortest just because of that triple bond. So once again, anything that has a triple bond is the shortest. Anything that has just a single bond is the longest bond length. Okay. So let's move on to the next question. Belinda states, hi, Melissa. My question is about pH. The pH of a solution containing our hydronium ion. So hydronium, by the way, is just acid concentration, or they also state it as H+, just in case you see that. And they give us our acid concentration is 1.0 times 10 to the negative 7th molarity, and label the solution as acid, basic, or neutral. How do you solve that? Got it. So what you're going to look for and how you really solve any of these, whenever they give you your overall concentration of your acid, you're going to plug it into your pH formula. So your pH formula is negative log of the concentration of your acid. Okay. I'll show you how to do this. I'll also show you a trick. So one thing with this, because they give us the amount of our acid concentration, all we have to do is plug it into the formula. So I'm going to plug that in. So really we're doing negative log of 1.0 times 10 to the negative 7th. And let's plug that into our calculator. So negative log of 1.0 and 10 to the negative 7th. And that gives us 7. And I'll tell you how I knew right off the bat why this was the case. So one little trick for you is whenever they have this first part where it's just a 1, so whenever this is just a 1, okay, this is when the little trick applies, is I'm just going to look at this exponent here. And this exponent is actually going to tell me the pH, it's going to be a positive value. So the pH would have been 7. If this were 8, then the pH would have been 8. If this were 2, then the pH would have been 2. And see the trend. So that's what negative log, this whole entire pH formula really does. And like I said, it's only when that's a 1.0. Now, to help you understand, is this neutral, acidic, or basic? The main thing to look at, looking at our pH scale, 7 is always neutral. Anything above 7, so think of it 8 to 14 is basic. And then anything below 7, so to 1, is acidic. So in our case, it's going to be neutral because our pH was 7. That's how you apply that. Okay. And then Crystal asks, what is the effect of molar mass on the speed of reaction? Let's see how I can answer that question. I just want to understand it a little bit better. What is the effect of molar mass of the speed of our overall reaction? Specifically, the speed of our reaction depends on, I wouldn't say it depends on molar mass, it depends on concentration. So I don't know if that's what you were asking. I can see if there's another type of question that I can get into, but specifically it covers, hold on, let me see if I can find something for you, but effect of molar mass, but specifically it's our concentration, it's our temperature, it's adding a catalyst. Those are things that overall affect our speed of our reaction or the reaction as a whole. And you can kind of see what else I can get to that. It does depend on the particle size and the mass. So I'm assuming that's something that we can look at. Let me see if I can find anything else. But typically it's just concentration. I wouldn't say it's molar mass. Let me see if I can find anything. But I'll keep looking at that. But yeah, that's actually what I would state is, I don't want to necessarily say there's no effect, but I'm just thinking what I want to throw. I would say it could influence it. If we're looking at the particle mass, it could increase it. But like I mentioned, I'll state that yes, like with molar mass specifically, we can think of the mass and the particle of whatever reactant we have, right? So if we increase that, then it's essentially like you're increasing the concentration. So it could speed up, it could affect the reaction, meaning think of it this way. So I believe you're talking about kinetics. So if it's like, let's say 0 order, actually, that's not going to do anything. But if it's, actually, let's do first order. If it's either first order or second order, then if we were to increase the concentration of our reactant, then that definitely speeds up our overall reaction. That's something to kind of look at, and it's specifically for first order and second order. So I hope that makes more sense, but specifically molar mass, I would really call it concentration. That's something that affects it. With molar mass, I'm assuming it's talking about the size of the particle. So yes, it could speed it up. And I'm going to look at another question. If I've already answered your question, guys, I'm trying to at least answer one question per person just to be as fair as possible. So I am going to answer someone else's question. Gas stoichiometry. Morgan asked gas stoichiometry. I'm just going to try to find your questions. Balanced, where was it? Oh, it's there. Okay. If an airbag has a volume of, so here we have a volume of 36 liters and is to be filled with nitrogen gas at a pressure of 1.15 atmospheres and a temperature of 26 degrees Celsius, how many grams, so we're looking for grams, of NaN3 must be decomposed? So let me look at, if an airbag and a volume of liters and it is to be filled with nitrogen gas, that's what I wanted. This is a pressure of N2. Okay, and then they give us a balanced equation. Let's find it. I'm just trying to piece together because it like broke it apart. There it is, 2NaN3, 2Na plus 3N2. Okay, there are the questions. All right, so we're looking for our grams. This is gas stoichiometry. What I want to do first is, with the given information, essentially think of this as this is only pertaining to N2. So However, we want grams of a completely different compound. So what we're going to do is we have to figure out the moles of N2 to then be able to do a mole to mole ratio using our balanced equation to finally get to the compound that we want. So what I'm going to do first is I'm going to use the ideal gas law. So using PV equals nRT, and then given this information, I will plug that in a second after I change the unit. And then I'm going to solve for N, which specifically would be the moles of N2. So let's go back, and remember with temperature, we always want it in Kelvin. So I'm going to add 273 to convert it to Kelvin. So 26 plus 273 would give us 299 Kelvin, and then everything else is in the proper unit. So I'm just going to plug that into the formula. So let's go ahead and actually solve for moles just to make this easier to plug in. What I'm going to do is I'm going to divide RT over to both sides. That cancels. And then our formula here that we're using is N is equal to PV over RT. And then I'll plug everything in that we're given. So our pressure is 1.15 atmospheres times the 36 liters divided by our R is 0.0821 liters atmospheres divided by moles times Kelvin. And then I'll times this by our Kelvin, which is our temperature, so 299 Kelvin. There we go. And then this will, the reason why we're changing everything to the proper unit is just because our atmospheres, liters, and Kelvin will all cancel, and we're left with moles, which is what we want. So let's do the math. So doing the first top part, 1.15 times 36, and I'll divide this by these two multiplied. So 0.0821 times 299. Our moles is then 1.69 moles of N2. So the next step is to do a mole to mole ratio using our balanced equation to change our compound to the one that we want. So we're going from moles of N2 to moles of NaN3, I believe. Yeah. So I'm going to take this 1.69 moles and I'm going to do a mole to mole ratio, placing the moles of N2 on the bottom so they can cancel, and moles of NaN3 on the top because that's what we're looking for. So let's go back to our balanced equation to tell us how much of each we have. So we have 2 moles of NaN3 and 3 moles of N2. So that's what I'm going to put here. We have 3 moles of N2 and 2 moles of NaN3. So let's figure that out. And then from there, this wants grams. Actually, I'm not done just yet. I'm going to go one step further just because we do want grams. So this is 1 mole of NaN3, and I'm going to figure out the molar mass of NaN3. All right, so Na, I believe, is 23, or really 22.99. It's 22.99 plus there are 3 nitrogens. So 3 times 14.01. Figuring out that molar mass, this is 65.02. And then the last step here is just to multiply the top and divide by 3 after. So multiplying everything on the top together and dividing that by 3. And our final answer is 73.255. I'm going to round in a second, but this is what I get so far. I'm going to go back to the given and see how many sig figs we should round to. So just looking at the least amount of sig figs, our least amount is 2 sig figs. So I'm going to round to only 2 sig figs, rounding this to just 73. So our final answer is 73 grams of NaN3. All right, that was our gas stoichiometry. If you guys need any more help with gas laws or gas stoichiometry overall, I do have detailed notes on it that I feel are really, really good because truthfully, I wish I had that when I was in school and I was taking these classes because they cover all the different topics in one. You know, it doesn't take a whole week or even month to explain it. It's like right there on that paper in that packet. So definitely check that out. It's in the description box of this video, and I'll see if I can place the link for gas laws, the detailed notes. All right, let's look at our next question. Laura says, how do you know which has a greater melting point in a compound? How do you find that? Okay, so what you're going to look at specifically for melting point is a lot of times we look at intermolecular forces, or we also look at the overall mass of the compound. Like, let's say if they're this, like the same intermolecular force. And what I want you to think of, going back to intermolecular forces, we know the first one is ion dipole. It's the rarest one. The one that you typically see is hydrogen bonding. Did not spell that right. Hydrogen. Come on. Bonding. And then the next one is dipole-dipole, and I'll explain real quick what this is. And then the weakest one of all is the London dispersion. London dispersion. Okay. So whatever has a higher, so the higher we're saying melting point, the higher the melting point, and actually really the higher I'm going to say IMF, just intermolecular force. The higher the intermolecular force, the higher the melting point. And what I want you to think of with melting points, essentially, since we're trying to melt something, or really what we're doing with heat is we're trying to break those bonds. So by breaking those bonds, essentially, if it is so stuck together, right? If it's so clumped together or so strong, that bond, that makes it a lot harder to break. That's why we're going to need a higher melting point. But if something is easier to break, so like let's say if we had something that was like London dispersion, an example of London dispersion is anything that is nonpolar. Like let's say CH4, that's a really good example. Same thing goes for, let's say if this were I2, that's another example for you. That would have been really, really weak. And then if we were to look at, let's say, a tiebreaker with this, you would look at molar mass. Whatever has a larger molar mass is going to have a higher melting point because it's harder to break. And then whatever has a lower molar mass is going to have a lower melting point. So that's what we really focus on. For more information, by the way, with intermolecular forces, if you're not too familiar with that, I do have a video explaining every single one. And then I even go into examples of how to rearrange it in increasing order. So the concept here is just the higher the intermolecular force, the higher the melting point. So it's called intermolecular forces. I'll place the link in the chat. Definitely check that out. That's going to help you understand how to figure out what's the strongest and weakest intermolecular force. All right, let's go to another question. Kira says, how do you solve for pH when given OH? Okay, so we're going to look at a few formulas here. Let's say if we're given our OH concentration, and let's say if it were, make one up, 3.5 times 10 to the 8th, sure. Okay, and let me make sure that this even works. Just making it up off the top of my head. So let me make sure that this works real quick. Negative log of that. 3.58. That's what I thought. Negative. I want to give you an example that actually works, because these numbers are a little bit different. That would have been that. Subtract that by 14. Yes. Okay. So this works. Let's say if we're given our concentration of OH. And we're trying to find our pH, right? So finding pH. What you're going to do first is you're going to actually find your pOH. And how we do that is by plugging it into our formula, which is negative log of our concentration of our OH. So all I have to do for right now is just plug in that OH concentration that was given. And then I'll do that. And when I do that, this gives us our pOH, which is 7.46. Okay, and then that would be your first step. Step number 2 is to use this formula. So there's a formula that's known as pH plus pOH is equal to 14. This is always going to help you, and these are always the steps, by the way, to take when you're given your OH concentration and you're trying to find your pH. You're first going to start off with finding your pOH using this formula. Then you're going to plug what you just found into this second equation and then solve for pH. So that's what I'll do here. Solving for pH, I'll plug in that 7.46. And then the last thing is to get pH by itself. So we'll subtract 7.46 from either side. And then that'll finally give us our pH, which is 6.5. 5, 4, and that would be our pH, right? And then note that, just a little extra thing for everybody who's on pH, we know that since this is below 7, this is going to be a little bit acidic. All right, but that's what you would overall look at for figuring out this question, just 2 steps. Okay, and then Kevin asks, how can I identify molecules that are polar or nonpolar? All right, so great question. Now, you're going to have 3 main factors to look at polarity. So our first one, when we're looking at polarity, is symmetry. All right, so these are what I'm going to cover right now is just the main factors to figuring out, is it polar or not? Okay, so if something has symmetry, so yes, it's symmetrical, then that means it's nonpolar. If something is not symmetrical, then that means it has a possibility of being polar. Okay, there's more to it, but it has a possibility of being polar. So, for example, if we were to have something like, and actually, let's look at this. Cl, 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 sure. Something like this, okay? Whenever we're looking at polarity, essentially what we're looking for is we're looking for something known as a dipole moment. And what I want you to think of, and how I typically teach this, is imagine there's like a tug of war, okay, between 2 different people, or really 2 different elements. And you're trying to see who's going to win that tug of war or pool of electrons. And if someone actually wins that tug of war, then that makes it polar. So in this case, think of this as all of these chlorines are the exact same person, and they have equal amount of strength. So if they're pulling in opposite directions but equally, no one's going to win. So essentially the concept here is that all of them are going to cancel each other out, and that's why it makes it nonpolar. So anytime we have symmetry, automatically that makes it nonpolar. Okay, so however, if it were polar, and let's say if we had something like, I'm going to change this up a tiny bit, something like this, then though it looks more symmetrical, and by symmetry, what I'm really talking about is all of the outer elements are the same. Okay, that's what I mean by that. Like, yes, you guys can get technical with this, right? And say, okay, well, we can chop this down the middle and that's symmetrical. That's not necessarily what we're looking at. Specifically, we're looking at who's going to win that tug of war. So think of it as chlorine in this case would have won, making it more polar. And that goes into the next question, or the next factor, which is electronegativity. And I'll explain why this structure won. So electronegativity, there we go. Okay. Essentially what we're looking at is whatever is closest to fluorine, because our trend is as we move across the period and up, that is increasing electronegativity. What electronegativity is the concept of an element wanting to attract another electron. So how well that element attracts another electron. So fluorine is going to attract another electron very well. That's why it's very electronegative. It's actually the most electronegative. So that's why I like to look at it as whatever's closest to fluorine, that's going to be the best one to look at. Now, think of that as the ones that are most electronegative are the bodybuilders. They're the strong ones, okay? So chlorine in this case is going to be a lot stronger than hydrogen that is completely on the opposite side of the periodic table. So that's why this is polar, because it wins that tug of war. And the last thing, the last factor, are electrons or lone pairs on your central atom. So lone pairs on central atom. Okay, I know this is going to help a lot of people out if you guys are on this topic. So lone pairs on the central atom, let's look at something like, let's look at a few of these. Okay, and let's say something like that. Okay, so something like this, if we were to have either of these structures, the fact that there are lone pairs on that central atom automatically makes it polar. So it makes it so much easier to just know, okay? So anytime you see those 3 factors, it'll really, really help you out to understand, okay, is this polar, is this non-polar? And as mentioned with the symmetry, if they're all the same all around the outer elements, then it's non-polar. Hope that makes more sense. Let's move on to the next question. Yeah, let me go back. Okay. Maya asks, as I take a sip of water. All right, so Maya is asking, a flask of a volume, let me start writing this down, a volume of 149 milliliters is filled with a vapor of a liquid at a given temperature, so 95 degrees Celsius at 0.0. The mass of the vapor, so we're given the mass, is 0.375 grams, and then our pressure is also given. Okay, so our pressure is 0.974 atmospheres, and we're looking for the molar mass. Okay, so our main thing here is just looking for the molar mass. Recall that your molar mass is grams per mole, right? So the main thing here, let's see what we're given. We are given the mass already, all right? So let me actually draw this out to help you understand this a bit better. There's really two main steps here. So the main step is to get our moles, okay, to get the moles. That's why they're giving you pressure and temperature and volume, so you can use PV equals nRT or the ideal gas law to figure out your moles. And then what you're going to do after is note that they actually already give you the mass. So we'll plug that in after, and then the last step is to divide. So that's all we're going to do here. So the first step is to use PV equals nRT and solve for n. Okay, so we're going to solve for n and make sure that all of your units are in the proper unit, which they're not. So let's start off with that temperature. Let's add 273 to get that into Kelvin, and then we'll convert the volume as well to liters. So 95 plus 273. This gives us 368 Kelvin, and then our volume, let's change this. So divide this by 1,000 milliliters per every 1 liter. Really what we're doing here is dividing and moving this over 1, 2, and 3. So this is 0.149 liters. Okay. I'm going to plug everything in now that it's in its proper unit, and let's plug that into PV equals nRT. What I'm going to do again is rearrange this formula by dividing that RT to either side, so that cancels out, and we have N is equal to PV divided by RT, and we'll plug everything in that we have so far. So finding our moles, our pressure was given, that was 0.974 atmospheres. Our volume that we just converted was 0.149 liters. We know the gas constant is 0.0821 liters, atmospheres, moles, Kelvin. That's why we had to change all of our units to match pretty much this constant, okay? So then now our temperature was 368, I believe I said. Yes. Okay, let's multiply everything out and then divide. And we're almost there. So 0.974 times 0.149 divided by 0.0821 times 368. And then this is going to give us 0.00480 moles. Almost there. All right. So the last step really is we're really given our grams in the very beginning of the question. All we're going to do now is plug everything in. And remember, molar mass is grams per mole. So we are given our grams, which was 0.375 grams. I'm going to plug in this moles that I just found. So that's 0.00480 moles, divide, and that's your molar mass. And then, of course, we'll check the sig figs. So 0.375 divided by 0.00480. That gives us 78.125 grams per mole. And then let's double check our sig fig count. So I'm going to go back to the given. So going back to all of the givens, our least amount of sig figs really was 3. So I'll round, because everything was 3. I'll round to 3 sig figs, and then we're done with this question. All right, so rounding to 3 sig figs, I'll stop right here at the 1. So our answer is 78.1 grams per mole. That's it. Okay. Next question. Yesenia says, how do you know what law do you use to solve? Good question. So the best way to this is pretty much my trick for you guys, is the best way to look at gas laws and know which formula to use is to figure out what you have. Okay. So that hints to what you are, like what formula you should use. Like, let's say if you're given two different pressures. Okay. Like, let's say 1 atmosphere versus 0.5 atmospheres. And then you're given one volume, 50 milliliters, and then you're asked to find your second volume. So this just hinted at which formula. Well, that gives us PV times PV, really. All right, so there's that formula. And then next, so Boyle's law. And then next, if you were given a lot more, if you were given the second volume, and let's say that's 100, and then you're given actually just one temperature, and you're asked to find your second temperature. So let's say this is 298 Kelvin. So if you're given all of this information, then the fact that we have so many pressures, volumes, temperatures, and pretty much we have everything, that means it's going to be our combined gas law. So that is going to be the best way to look at this, is to first identify what do you have. Okay, so I literally like to always do that with all my questions, is to identify the given and then what you're asked to find. And then that basically tells you, okay, well, what formula do I have to use? Because it's essentially hidden within this. All right, so that's going to be the easiest way. Okay, next question. Jennifer asks, what's the easiest way to remember polyatomic ions? Okay, so the easiest way I would state is to write them over and over. Personally, I don't feel that flashcards are the best. That is how I feel overall. But I've noticed that with my own students that flashcards don't work. I personally think that flashcards are best for just vocabulary rather than actual like symbols or whatnot. So what I would do is I would write down all of the polyatomic ions, and let's say, so I would actually list them in order. So like, let's say NH4 plus, that's ammonium. And then I would do OH minus, and I'd list everything according to the actual charge. So OH minus and cyanide and let's say NO3 and so on, NO2. And then that helps me remember how all of the charges, or what the charges of everything's going to be. Another trick for you, and by the way, I would keep ordering this, like SO4, actually SO3 and SO4, that's a 2- charge, right? Or carbonate, which is CO3, which is a 2- charge. And then lastly, phosphates, PO3, phosphite, 3- and phosphate. So that's going to be the best way, is just to write it over and over again, and then making sure to, like I said, put those charges in order. The other thing that I've done in videos is I've explained how there's this is a way to kind of cut your memorizing in half, is the fact that if you were to have, let's say, phosphite, anything that ends, so I'm looking at the ite and then phosphate, and I'll show you the trick here. Phosphite versus phosphate, you'll note that the ates are always going to have one more oxygen than the ites. So in this case, PO4 is an 8, so that has one more oxygen than the ite. And that's always the case. So like, let's say if we were to look at sulfate, that once again has one more oxygen than sulfite, which is O3, and nitrate, so NO3 and NO2, nitrite. So instead of memorizing all of them, you can just remember one, and then knowing, okay, well, the ates have more than the ites, and how I remember that too is I ate more. So that just means there's one more oxygen than the ates. Okay, so, or than the ites, I'm sorry. So the ates have one more oxygen than the ites. That's the concept. So that's what I recommend. All right, next question. Let's look at Nayli. Calculate the pH of carboxylic acid and a buffer system. Okay, given that it is, and we're given a concentration. So we're given 0.125 molar solution of carbonic acid. And we're given a concentration of our salt. So 0.245 molar solution of NaHCO3. And we're given our Ka value, 4.2 times 10 to the negative 7th. Okay, so we're asked to find pH, specifically pH of a buffer. A lot of times whenever we're doing this, and actually really always when we're doing this, for the pH of a buffer, we have to use a specific formula. So our specific formula is going to be known as the Henderson-Hasselbalch equation, which is pH is equal to pKa plus log of, and this is going to be of our concentration of our salt, and then divided by the concentration of our acid. So we're going to have to get to that. And actually, we're given everything already. So far, we really just have to plug in. The only thing that we have to do initially is figure out what our pKa is, how we're going to do that. The formula for this is pKa is equal to negative log of our Ka value. So I'll plug that in and solve. So our pKa is equal to negative log of the given Ka value, which is 4.2 times 10 to the negative 7th. There is no need for an ice table for this question because we're not adding any acid, adding any base. There is no change. So an ice table, we only use that when there's an actual change in the buffer or change in the question. So since there isn't that, there's no need to use an ice table. So let's figure out what this is. So plugging this into the calculator, negative log of 4.2 times 10 to the negative 7th. This gives us 6.38. That's our pKa. So then now I'm going to plug this all into our formula here. So our pH is equal to 6.38. That was our pKa plus our log of, I'm going to put the concentration of our salt first. So that was 0.245. And then on the bottom will be the concentration of our acid, so 0.125. And then I'll figure out what that is. So I like to divide these two first, then take log of it, and then at the end add the 6.38. So 0.245 divided by 0.125. Then I'm going to take log of that answer. And then what you got here, by the way, was 1.96. So now I'm just taking the log of that value. And then that gives us 0.2922. I'm going to add that to the 6.38. And then we're finally done. So adding those two together, pH, I like to round to 2 decimal places. That's what the typical case is. This is 6.67. And that's our overall pH. You'll note that there isn't much of a change. So that's it. That's all we have to do in this question, is to really just know the formula and how to apply it all. All right. Let's move on to the next question. Okay. Make room. There we go. So Jacqueline states, or asked, how many milliliters, so we're looking for milliliters, of barium nitrate. Let's show what barium nitrate is, right? Going back to naming. So how many milliliters of barium nitrate? And we're given our concentration, which is 0.280 molar solution of barium nitrate. And we're also given, let's see, so are required to precipitate as barium sulfate, all the sulfate ions from 25 milliliters of 0.350 molar of aluminum sulfate. And let me double check my charges there. So aluminum is 3+, I believe. Yes, it is. And then sulfate's 2-, so this isn't balanced. So I'm going to move this 2 and that 3. So this is Al2 and SO4 3. Okay. All right. So we're looking for milliliters. A lot of times what we're going to do here, basically, we're going to go from milliliters of what we're given initially. Okay. So what we're given initially is that aluminum sulfate, and then we're going to make our way to finding milliliters of a completely different compound. So if there's a completely different compound, we need a balanced equation. So let's start there. So I always like to start with the balanced equation with these questions. Essentially, this is stating we have barium nitrate, Okay, and let's see what we're adding this to. Are required to precipitate, okay, as those two barium sulfate, all the sulfate ions from that. Hold on, I'm just trying to see what we're given. Aluminum sulfate. Just seeing if there's any trick to this question, but no, there wasn't. Okay, so all I have to do is predict the products and make sure everything is balanced. So what we'll do here is the inner with the inner and the outer with the outer, as you guys may already know. But we're going to start off with the metal first and the non-metal. So this is going to be aluminum with a 3+ charge, and then nitrate has a -1 charge. So this is going to form aluminum nitrate, but the nitrate will have a 3 subscript. And then next I'll move on to the outer with the outer, where the metal is first, which is barium, that has a 2+ charge, and then SO4 has a 2- charge. Those are balanced, so plus barium sulfate. And then let's just double check, is this balanced? And it's not. So we have to balance this out. This is a good little refresher of how to balance out balanced chemical equations using polyatomic ions. So what I'm going to do is just separate everything. The main thing with polyatomic ions, whenever they're the same on either side, I leave them intact. So I'm not going to separate those out, meaning I'm not going to put like a nitrogen and then an oxygen. I'll leave those together. And it makes it so much easier. But let's go ahead and balance this real quick. And then we'll move on with this question because I know it is a little bit longer. So barium, there's only 1. Nitrate, there's only 2 because of the subscript. And then aluminum, there's 2 due to the subscript. And there's 3 SO4s. Okay, and then for barium on this case, there's only 1. Nitrate, there's 3. Aluminum, there's 1. And sulfate, there's 1. So what I'm going to do first, let's go ahead and balance out, why not aluminum? So I'll balance out aluminum by putting a 2 in front. And when I'm doing that, it's like I'm distributing. So this is 2 for aluminum, and then this is 2 times 3, so 6 nitrates. And then next, that's really all that changed. I'll keep going. Now let's try to balance out sulfate. So I'll put a 3 in front. This changes everything. So this is now 3 for barium, and this is 3 for sulfate. And then let's go back to the reactant side and balance. So I'll place a 3 in front, and this gives us 3 bariums and 3 nitrates. Actually, 3 times 2, so 6 nitrates. And then next, we still want to balance out. Actually, everything else is fine. Perfect. We're done balancing. Okay. So that being said, because we will use this, that's our overall balanced equation. We'll use that in a second. But the first thing that I want to do is just change this to liters. So our main concept here is to go from milliliters of aluminum sulfate. We're then going to get to liters of aluminum sulfate. And then next, using the molarity that's provided, we're going to use that as a conversion factor. So we're going to use the molarity to get to moles of aluminum sulfate, which then allows us to get to moles of a totally different compound by using a mole-to-mole ratio, using the balanced equation we just found. And then this is going to give us moles of barium nitrate. And then we'll get to liters. This is a very long question, I know. Get to liters of barium nitrate. And lastly, and we'll use the molarity that's provided. And then lastly, we'll get to milliliters of barium nitrate. Okay. Let's start. So that's the general concept. Let's start off with what we have. Let me go see if I could see the question again. Okay. Because this is going to take a second. So we're starting off with 25 milliliters of aluminum sulfate. I'm going to change this to liters by dividing by 1,000. And once again, this is still aluminum sulfate. Okay, I'm going to just put aluminum, but I really mean aluminum sulfate on top. I'm just running out of time. And then what I'm going to do now is I'm going to use here, I'll actually put it. I'm going to use the molarity that was provided. So we're given the molarity of aluminum sulfate. So that 0.350 is really moles per liter of aluminum sulfate. That's what I always want you guys to think of molarity when we're given it as a question, or really given it in this type of question. So 1 liter of aluminum sulfate, and then on top will be 0.350 moles of aluminum sulfate. Next, we can change this, there we go, to a multiple ratio to get a completely different compound. And what we'll do here is we're going to go back to our balanced equation in a second, just looking at barium nitrate. Let me go back to the balanced equation. We're going to look for the moles of barium nitrate per the mole of aluminum sulfate. So let's see what we have. So there are 3 moles of barium nitrate per every 1 mole of aluminum sulfate. So that's what we're going to put in here. So we said 3 to 1. And then next I have to use the molarity of barium nitrate, and I'll put the moles on bottom. So we were given our molarity was 0.280. Think of that as moles per liter. I'm going to flip that, and I'm allowed to flip that. So really the moles is going to stay on the bottom because that's the moles of barium nitrate. And then on top will be 1 liter of barium nitrate. And then the last step is to just convert this to milliliters by multiplying by 1,000 milliliters per every 1 liter. Okay, long question, I know. So what I'll do is I'll multiply this all out. So I have 25, I know it's hard to see, 25 times 0.350 times 3 times 1,000. Okay, and I'm going to divide the bottom first. So on the bottom we have 1,000 times 0.28. Let's see what that gives us. 0.28. All right. And then this is 93.75 milliliters. I'm going to go back and look at my initial values. The initial values were all 3 sig figs. So I'm going to round to 3 sig figs. So I'm going to round up. So this is 93.8 milliliters of barium nitrate. All right. So that would be our final answer. I'm going to see if I can answer anything else, but I know that they're going to be a little bit longer. Let's look at Rajadeep. Let me see if I could at least give you a hint for that. So if you pass an electric current through water, you can break it down into its elements. Draw what products of electrolysis of water would be, and is it a physical or chemical change? Can explain the difference between physical and chemical. I can explain the thought of physical and chemical change. So when we're looking at something that has a physical change, we're really just looking at its state of matter. Did it change? Meaning, did it go from a liquid to a gas, or a gas to a solid? So really it's looking at just the kind of like the appearance of that change, meaning like, did it go from a solid, a liquid, or a gas, or going back in any of that? So that's one thing that we always look at when it's a physical change. If it were a chemical change, then heat is most likely applied. We think of it as a chemical change is actually changing the chemical composition of it. And what I want you to think of with that, a chemical change is essentially, let's say if I had water, okay? And if I were to change water, really, then what I want you to think of this is I'm essentially just breaking this apart. So if I'm breaking the chemical composition of water into just splitting it apart, then that would mean it's more of a chemical change. Anytime we apply heat, that typically is a chemical change. Anytime they state something about resting. But to kind of look at your question, because you're looking for the products of electrolysis of water, let me see if I can find real quick, because I know this is a longer question. I won't be able to draw it out, but that so far is the difference between physical and chemical. Let me see if I can find anything real quick and just kind of look at an example for you. Let me see what I can find, because it is a lot larger. But overall, the electrolysis of water, we know it starts off as a liquid. So this is the balanced equation. So it starts off as a liquid and then it moves into, it's going to end up breaking apart. And actually that's what I was doing here, right? I was stating it was water and it's breaking apart into H2 and O2. Of course, we have to balance this out. So this is where I'm going to take this from real quick. What you would do is, since this is a liquid, this is turning into a gas. And then from there, what I would do is I'd obviously balance it out, of course. So this is 2, and this would have also been a 2. So that's the balanced equation for it. That is the products of electrolysis of water. Specifically, what you would also kind of continue doing is writing the half reaction cells. So let's say like this is one, and this would have been your, it's an H plus. This would have been your oxidation step. And then the other one that I'm going to draw is, or write out, is the reduction step. So that's something that they can look for. I would have stated it is more chemical just because we are breaking and decomposing this. So it doesn't just change into, pretty much we are adding different things here, but I would state it was more of a chemical change because we're not just going from a liquid to, let's say, a vapor of just water, right? We're not going from there. We're completely breaking apart that water. All right. So that's the general concept. And actually that pretty much answers your question there. Okay, guys. So we went through a lot. I know. So as to kind of mention to you guys, if you just, came in a little bit later, thank you so much for being here and joining. Now I want to explain another really exciting thing that I'm doing to help you guys with specifically thermochemistry and overall to help you in class. I've been getting a lot of requests with tutoring and if I do online tutoring, and I decided to open that up. And so you'll note on the screen that there's a specific website. It's howtopasschem.com. Make sure to check that out to reserve your spot for tutoring with myself. And what it's going to be on thermochemistry, and I'll be covering all those different topics, whether it's Hess's law, bond energy, calorimetry, and enthalpy stoichiometry, specifically enthalpy stoichiometry. So all of those concepts, if you're currently doing thermochemistry, definitely make sure to check out that link. And then if you don't see the topic that you want, then I keep checking because I will be putting different topics along the way. I'm considering doing possibly another Saturday, doing electromagnetic spectrum or Lewis structures. I'm not sure just yet, but I am planning on doing this from pretty much every single Saturday from here on out. So it is next Saturday that I will be doing an online tutoring. It is group tutoring, but it's a lot smaller of a group. So it's an hour of me teaching you all these different topics in thermochemistry and pretty much telling you what you need to know for your test. And then in the last 30 minutes, you would get, it's a Q&A. So you get a lot more of your questions answered. In total, it is an hour and a half, so 90 minutes. As I mentioned, the first hour is me teaching, and then an additional 30 minutes thereafter is Q&A. So make sure to check that out, guys. And I'm excited to hopefully see you guys Sunday and Sunday and Saturday. So I'll see you next week. All right, guys, have a good one.